Okay, this is the normal trying to figure out whether or not the stream is actually working period. So give me a moment while I get some feedback on whether or not you can actually see me. Hey, it seems to be working now. Fantastic. That has to be the quickest stream start we've ever had on this channel. Wow. And someone says hello. Hello there, the red. Everything's working fine. So, this is obviously the Wanptek KPS305D I reviewed not very long ago at all, and I've been trying to kind of figure out how to fix the noise issues on the output, and in doing that I've figured out that I am absolutely awful at measuring switch mode power supply noise unless it's something battery powered. So most of this stream is probably going to be me trying to get this Rigel scope to measure noise on the power supply with some kind of reasonable accuracy and repeatability, and probably going to be testing to compare some with my TTI EX752 up there. So to get you guys up to speed on what I've actually been doing thus far in the experiment, I have built this little PCB. Let's get some focus on that. So this is first test filtering device for the Wanptek. Yeah, it's going to be a Wanptek from now on, and it's just random supplies gathered from this switch mode power supply here. So we've got one big choke, then a big electrolytic cap, then a smaller choke for high frequency stuff, and a couple of smaller caps on the output, and this does absolutely nothing, which is making me think that my testing methodology is entirely wrong. And I'm going to try and remedy that, because I would expect to see at least some form of result when adding that much inductance and capacitance to the output of a power supply. So in case you want to laugh at how wrong I'm doing all this, and if there's some expert out there, I'm pretty much just using a stripped coax to get as much shielding as possible going straight into from the scope to the power supply. This is both ends of a wire. There's nothing smart in there, and I have noticed that this does reduce interference significantly compared to using a proper scope probe. Even in ×1 mode, my probes have about 100 ohms in the wire, and I don't have any proper ground clips, so I've been using this rather horrible thing to get the ground, and that's obviously not going to work very well when we're dealing with high frequency, low amplitude stuff. I have also tried just disregarding the ground clip altogether and using the BNC cable to ground this, with ground only being connected in the BNC on the scope, and that just makes everything even worse. So I'm figuring I'm going to go with a straight BNC. That's been giving me the most repeatable results thus far, and we'll go from there. So I have actually got out of frame an inverter with batteries, so I can run either the scope or a power supply straight off of battery power with no real ground connection at all. And I tried doing that with a scope for a while, and that made everything worse. I haven't tried doing that with a power supply yet, since this thing only has one capacitor leading down to ground from the secondary. I'm figuring this one's probably not gonna couple as much stuff down to ground, so we might get better results if we just run this off of the inverter with no real ground reference and the scope on the mains. So let's just start by doing that, I guess. Or rather, let's just start by getting a baseline for this current setup. And this is where it's going to get absolutely horrible for you guys, because there's no way in hell you're going to be able to see the scope properly unless I start mucking around with the cameras way too much. So let's just get everything set up. Trigger. I will trigger from channel 1, and we will couple it DC. Yeah, that's good enough. Okay. Yeah. Hang on, I'm just gonna rewrite that camera to just shoot the scope screen, because that's just gonna make everything so much better. And as always, of course, I've got my proper expensive camera sitting there, which is just acting as a stand for my cheapo webcam, since I can't afford a proper HDMI capture card. I'll just move this over here and shove that somewhere, and perhaps we can clamp this onto one of these lamps. That would be very handy indeed. And I think we've even got some software zoom capability on that, so let's see if we can get real fancy here. And how do we do this? We go there, and we go there, and then we'll wait for the Logitech driver to load. Wham! Isn't that fantastic? Oh, that's decent enough resolution even. Can we get a bit less exposure? Can we get a bit more less exposure? Yes, we can. Wow, look at that. There we go. That's useful enough. You could simply isolate the ground wire from the input power supply to exclude any ground loop noise. Yeah, I've tried doing that. It doesn't help enough. Probably because we've got caps trying to couple to ground from the 8-bit of the power supplies in these things. I'm not sure. I'm way too much of a novice on these actual things. So let's get a baseline for this stuff anyway before we actually move on. So we've got this thing powered up now, and I have got my scope probe, and this goes to a resistive load, currently 8 ohms, so we're going to be drawing some current out of this power supply to just load it down ever so slightly. Hey, look at that. By just connecting this up, we're already picking up some noise. That's a lot of noise. Where's that coming from? Is that going to be my lights? Let's make it dark in here. Okay, it's not my lights. Well, that's a very distinct noise actually. 100 millivolts. Okay, so if we short the probes together, they say. Once we get a low impedance on the plugs, we should hopefully not see any of that. But I am surprised though at the magnitude of that. I mean, what? Perhaps we would be well off actually using a shielded wire to connect to the load, because that's a lot of noise. Oh well, what happens if we just plug it in there? Yeah, that kills the noise. So that's just yeah, I'm running the test load lead right over a laptop. That's probably got something to do with it. Oh well, let's turn the power supply on, and in fact let's keep it off for a second and make a small note of what our noise is when we're just sitting idle. If I can find some paper. I used to have a note book for this kind of stuff. I don't anymore, because I do not know where it's gone. There we go. And a pen. So this is a channel where I plan everything very properly in advance. Who needs papers when one has tablets and magic markers? Tablets? I don't have tablets. What are you talking about? And by the way, the audio on this stream is going through an entirely different setup than it's ever have before, so I'm hoping it's decent. No one's been crying as of yet. Anyway, let's get some more scale on that. We've got 50 millivolts per division and 50 microseconds per division. Do we have anything? If we zoom out, no, this is pretty clean with a power supply off. So, unless I'm sorely mistaken, this should account for most grained noise, since we have a grained loop between the escape and the power supply already set up, since both are connected up to the power grid. So, in my mind at least, which you should not quote me on this, most of the noise we see when we turn the power supply on should actually come from the actual power supply. But on the other hand, the power supply could be incredibly noisy and trying to push a bunch more noise onto the power grid, so yeah, it's a bit confusing. We'll find that out. But we're sitting at I was jumping around a lot actually. We're not really triggering anything, so let's trigger. Now there's a bit of crap on the line. A bit of crap. You can see those little pulses there. I'm not entirely sure what's causing those. What happens if we disconnect the cord to the power supply? Nothing. So we're probably going to have to deal with those. But they're not major by any means. We're sitting at just jumping around between 15 and 30 millivolts. So we'll call that 30 millivolts of just shit on the line while we're just sitting idle. Idle. 30 millivolts. PSU off. That's some kind of a baseline. Sounds much better than the last stream. That's great. We don't have any noisy gating this time. Laptop screens and regular screens are magic marker friendly too. Oh, I see what you're getting at. I see what you're getting at. Anyway, let's turn the power supply on. Now that does give us a significant difference in our waveform. So let's see, I think we're in peak detect mode. So that should give us a rather negative forecast on this. Where do you go? That's in the acquire menu. No, we're in normal mode. Okay, well, we'll be doing normal mode. Let's write that down. Normal. I'm too bad at scopes for using peak detect anyway. It's just going to confuse me and give me the wrong results. So this is set for 12 volts and is drawing about 1.5 amps out of it. And we're currently getting around about 100 millivolts of noise. Perhaps we can trigger a bit better on some of this stuff. You see, this is why noise measurements are so horrible, because we're getting entirely different results than I got when I was actually shooting the review, even though I was using pretty much the same exact setup. And 100 millivolts, that's not even too bad. Oh god. The encoders on the scope are getting dicky again. Ah, yes, and now we're seeing something I saw while I was testing earlier. Let's see if we go to the trigger menu and choose the source as AC line. We're getting this weird kind of pulsing AC waveform there. You can see these big blocks of noise are very well synced up with the mains. Since we're triggering off the mains, we'll get bzzzt, block, bzzzt, block. So that's a bit disconcerting, which is why I'm thinking that my tests for this aren't very accurate at all, actually. And if I change the memory depth, everything turns different. Okay. Oh yeah, we cannot adjust our trigger level while we're triggering off mains, so let's just do channel 1. It looks better on the deep memory, so we'll go with that. That seems to rectify the... Why is the trigger not in the reset to the center, please? So it starts to get the scope somewhat well set up. This is looking like proper noise rather than random main C crap. Yeah, this is starting to look like something you'd get out of a switchmode power supply. If we turn the power supply off, we're getting some more of that 50Hz main C stuff running around. Oh, that's looking awful. That's with power supply off. But it's still sitting at about just over 30 millivolts. What? Why did that go away for a moment? What's going on? Why did that go away for a moment? Oh well. We're getting just about 120 millivolts of shit while we've got the power supply turned on and giving a 1.5 amps out at 12 volts. So let's just write that down. Let's say 110 millivolts of random noise and little tiny switching pulses in there. Oh god, this encoder's gone. This encoder is getting fucked. This encoder's gone entirely horrible. Oh god, what's going on? I think this coop's become very confused as to where the encoder... Oh, there we go. No. Stop jumping around randomly. Oh, for fuck's sake. Okay, that seems to be actually working now. Scope prepare video incoming. That would be very boring. You just take it apart and disassemble these and clean them out because the grease is leaking all over them. They're not very good quality encoders. I've done it once before. That's why I got the scope for free. Okay, so we've got about 100 millivolts of ripple at 1.5 amps at 12 volts. What happens if we increase the load? Well, we'll get a bit more. It's jumping around so annoyingly. We should probably be doing all the measurements at a rather wide time scale. We do catch that weird AC crap coming through. That is so annoying. I'm not sure how to rectify that. But yeah, we'll go with the 8M load, so let's see what happens with a roughly 110 millivolts noise figure if we move the power supply to an inverter rather than actually having it connected to the same AC outlet strip as the scope. We can also give you a better view of the scope there. Back in a sec. So just going to grab this power cord and plug it into the inverter. And that's the entirely wrong power cord. So this is a pure sine inverter which has an extremely clean output, so we're not going to see any issues coming out of the inverter, I would not think. But now we are getting a significantly higher noise figure, and I'm going to guess that our 50 Hz crap is a lot worse. So much worse. Could the noise be oscillations from the load, or is it just a dumb resistor? It is just a dumb resistor. So we're not going to have any noise coming out of the load at all. There's no risk. So let's just drop that down while we're at it. That is kind of similar-ish time scale. Yeah, that's close enough to what we had. So power supply on inverter, 1.5 amps. We're getting 170-ish millivolts. And what we'll get with power supply off, about 50 millivolts. Idle, 50 millivolts. So our noise is just generally higher with the power supply connected to the inverter. So let's just swap around and see what happens when we get the scope on the inverter instead. So now the scope's going to boot up on the inverter. And I will wait for that and write scope on inverter, and we'll do 1.5 amps and idle. And idle we're getting about 65 millivolts now. And this is going to be the worst result yet at 180 millivolts. No, that's even 190 because it's jumping around so much, because we're getting those weird 50 Hz artifacts. Yeah, 190 millivolts. Looks like I have quite a bit of background noise, but maybe the bench lights. No, because I tried to turn the lights off, and if I just short the lead sight, it will get rid of pretty much all the noise. Short lead to the scope would make more sense using coax. The lead into the scope is a coax. It's a rather high-grade coax as well. The noise obviously isn't coming through the lead to the scope, since shorting the probe sight causes most of the noise to go away. So we're getting really poor results doing it with the either device connected to the inverter. Now I'm going to test one final thing, and that is using the inverter, which is an online UPS, while also having that connected to ground. I'll just go plug that in. That's just making everything so much worse, isn't it? Jesus. Granted, that's going to a power outlet on the other end of the room. Well, that's just giving us useless amount of noise. So we'll just scratch that entirely. So our best results thus far are to just try and keep a short ground path between our device and the test on the scope by having them connected up to the same power strip, and just brute forcing the noise out of the equation, which isn't really a nice way to go about it. I don't like it. But I'm not sure what other options we've got with my rather crude setup here. I don't have any proper differential probe, and I don't feel... Well, we could actually just do one final test where we use a groundless power cord for the power supply. And here comes my very clearly labelled groundless power cord. Let's just plug that into the same power strip as everything else and put it to the power supply and see what we get. So our idle is still the same, and when the power supply is on, we're getting about... It's jumping around a bit. Let's do really wide time span there to get a good average. Yeah, about 120 millivolts. So our best result remains the one where we were actually having both the scope and the power supply grounded to the same outlet strip. Maybe try to limit the scope bandwidth. It is limited to 20 MHz. Bandwidth limit on. So that's a trap I haven't fallen into. But yeah, with that in mind, let's grab a few baselines for testing from my TTI EX752M power supply. So that's a high-end switch mode power supply, costing a lot of money. So we can at least use that to evaluate what a good power supply should perform like. So I'm just gonna go ahead and plug that into the same power strip as everything else, just to make sure that we're treating all the devices on the test equally. So let's just do this plugging. I'm very sorry that you're not getting very good video of this, because I do not have enough cameras, and I cannot be bothered to move the microscope camera. Oh boy, this is not the easiest thing to do. Oh, there we go. So now we've got my TTI connected up to the same post strip, so let's grab a few baselines at well, ranges which are within the capability of a cheapo power supply. So let's turn that on under the same settings. Hey, look at that. That is the waveform we're getting out of the TTI EX752M, powering the same load as the cheapy was. And we're clearly sitting just at our noise floor of about 30 millivolts. So that makes me feel that perhaps we've got a shot at actually performing some tests here. Oh, excuse me. Alright. So I will write down their TTI tests. TTI. And we will, well, let's just use the 8 ohm alone and do like 100 milliamps, 500, 1 amp, 2 amps, 3 amps, and 4 amps, because that's all it can manage. And we'll do the same thing for the Wanptek. So we'll do Wanptek 100M, 500, 1 amp, 2 amps, 3 amps, 4 amps, and then 5 amps, because it'll actually do 5. So draw a graph, which you absolutely cannot see due to my shitty camera. Oh well, maybe we can do it like that. Give you guys a shot at seeing what I'm doing. Yeah, that's more interesting. That is more interesting. So we've got ripple VPP there and VPP. Like so. And we will just allow the testing to commence. Wires going out of the way. And let's just write down the time base we're using for the scope. And let's do 20 millivolts per division, 20 MV/div, and 10 milliseconds per div. Just for easy remembering. And we will turn down the voltage to get 100 milliamps. I'll just adjust the voltage and go by the meters on the front panel. So 100 mil is giving us 20 millivolts of ripple on the TTI. Just about 20. And 500 is giving us, I'm going to go with 25. And 1 amp at 8 volts I'm gonna call that 29. 2 amps at 16-ish volts. That is 31 millivolts ripple, and 3 amps is giving us 34 millivolts, and 4 amps. I'm going to set it just under the current limit, so it's going to be like 3.95, so as not to put the power supply in current limiting mode. 3.97. That's giving us 40 millivolts of ripple. So that's our benchmark to beat. That's clearly something we can remember, or rather that is something we can measure with our setup, because if we turn everything down to 0, we're getting a baseline of about 20 millivolts. So anything above 20 millivolts is obviously coming out of the power supply. So let's turn the TTI off and do the Wanptek. And I need to fetch another power cord. Back in a sec. A genuine Apple power cord for your pleasure. Apple power cords are the best in the world because they're way softer than cheaper, more generic ones. Wanptek getting plugged in. And wires going into there. And we're almost clipping. So let's, current limits are at the max value. Let's just turn it up to 100 milliamps using the voltage controls, which are very finicky on this thing. Very finicky. Since we're just trying to put out about 800 millivolts. Oh God. The adjustment range of a fine controller is like less than 100 millivolts. This is impossible to get to 100 milliamps flat, but 110 will have to do. And we've got more ripple and noise than we can see. Audio may be a tad too hot. Sound great otherwise though. Okay. Yeah, it looks fine to me. Oh no, it doesn't look fine actually. Why is that not fine? I'll turn it down in OBS. Thank you for pointing that out. OBS is doing something retarded. Something absolutely retarded. Oh well. So, at 100 milliamps, the Wanptek is putting out 220 millivolts of ripple. 220. So that's about an order of magnitude over the TTI. So let's do 500 milliamps. There we go, 4 volts, and it's dropped down significantly. And we're now at, I'm going to call that 120. So let's do 1 amp at 8 volts. And we need to range up again because that's not measuring properly. 130-ish. So let's do 2 amps. .99. There we go. 2.00. We're still sitting at I'm gonna call that 120. 3 amps. 2.97. 99. 3.00. That's significantly increased our noise on the Wanptek to 185 millivolts. 4 amps. Oh, do we not have? Oh, we don't have a voltage to go that far up. So we'll do at 3.9 amps for the 4 amps, since that's as high as it'll go without having to swap the load. And now we're sitting at let's turn it down just a bit, so let's do 30.0 volts actually. That's 3.7 amps, it's close enough. And that gives us 275 millivolts. Which is quite a lot. That is a lot of noise. So for 5 amps we'll just swap the load down to 4 ohms and do it at a lower voltage. 5.00 amps. And that is very, very noisy. That is 500 millivolts of noise. Oh dear. That's not very nice. That is a very dirty output. That is a very dirty output indeed. So it leaves a lot of room for improvement on part of a Wanptek. So we'll draw a line there and see what happens when we actually connect up my little test board with some extra filtering components and see if it makes a difference. So I'll just redraw the graph. Wanptek VPP 100, 500, 1, 2, 3, 4, 5. And a line. And we can even do... Oh no. It would be kind of cool to plug this board into the TTI and see what it does, but the TTI has so little noise on the output that we would be so far into the noise of our measuring setup that we wouldn't be able to actually see anything. So we will put the load back to 8 ohms and feed some voltage into this. So 100 milliamps. I will write also filter V1, so we know that 100 milliamps. Oh god. The controls at low voltages for the Wanptek are ridiculously finicky. It's basically impossible to set an accurate voltage under a volt, which can be an issue if you're trying to do stuff like this. And now we can see that we've got an improvement because... Go away. Now we're measuring about 130 millivolts. Last time we were measuring 220, so that's better. Not good, but better. So let's do 500 milliamps. $500, and now we're measuring significantly less noise. We're measuring just about 60 millivolts. So that's less than half, well, exactly half of what we were seeing earlier. So we do have an improvement. 1 amp. .99, 1 amp. And at 1 amp, with the filtering board, we've got 75 millivolts of ripple and noise, which is again about half as much as we saw before. 2 amps. We already know by this point that you can improve the performance of this power supply significantly by just adding more filtering on the output, since the internal filter is undersized. So 2 amps, we're seeing 70. I'm gonna call that 75. It's jumping around. 75. 3 amps. Now that's making everything horrible. That's absolutely awful. Wow, what's going on? 165. Did we see that? Yeah, we had 185 on the 3 amps before. So we're seeing a bit of an improvement, but something's clearly happening once we go above either 3 amps or 24-ish volts. So let's do 4 amps. And we did that as 30 volts actually, because it can't quite reach 3 amps, so we'll scratch that. 30 volts. No, 4 amps. 30 volts. That is still 3 amps. 4 amps, 30 volts. And that's giving us 220 millivolts. And 5 amps we will drop down to 4 ohms. And adjust our voltage accordingly. 5.00, 20.6 volts, and we're seeing 350. So, with this little filtering board, we have seen a considerable improvement in the performance, but still not a very good performance at the higher settings. We saw an incredibly steep rise at some stage here, just going from 2 to 3 amps. So something's going on. Whether or not it's the power supply putting in more crap, or if it's this filter not really performing very well at high currents, that's an unknown. I would not expect this filter to cause issues at high currents, because I took it out of a PC power supply which is rated for tens of amps. But we do see the steep rise here on the unfiltered side as well, with 120 sticking pretty steadily from 500 to 2 amps, but getting above 2 amps it just rockets away. So something's a bit weird with the output of this power supply at higher currents, and we are seeing this rather curious pulsing pattern. Now that does look like something mains derived. That indeed looks like something mains derived, and we can probably prove that by just triggering off the mains, and this is going to sync up perfectly. Yeah. So we are getting mains derived voltage noise on the output at high currents. And that goes away when we go under 2 amps of output, pretty much. That's at 2.24, and as we approach 3 amps, it just gets noisier and noisier until it just goes out of hand when you runs at really high current. So what's actually causing that? Well, let's trigger normally again. So these are little switching pulses, most likely coming from the power supply, nothing else. Yeah, because it varies significantly when we alter the load of a power supply. So I'd wager that's what the actual switching frequency, or rather switching output of a power supply looks like. Odd that it would be modulating at 50 Hz though. I'm not really sure what would be causing that actually. I am not at all competent enough on these issues to make a good analysis of that. And why we're seeing these drops, it just strikes me as odd that this power supply would be modulating at 50 Hz. It could be that the input capacitors are undersized, but I think they're 270 microfarads. Now granted, for a 150 watt power supply, that is not a lot since they are connected up in series. So it could be kind of seeing a bit more ripple on the primary than it would like. But in such a case it would scale with output power rather than output current, and I think it's not scaling with output power. No, it's not scaling with output power, because now we're putting out 3.75 amps at 30 volts, which is more than we saw. Well, let's do 3.75 amps at a lower voltage, so now we're seeing about 200 millivolts. And if we drop the voltage and do 3.75 amps, oh no, we're seeing about the same. Yeah. So this odd noise is scaling with the output current rather than the output power. So I would not guess that this has anything to do with the primary side filtering capacitors, because they are under a lot less load now than they were before. That is an odd issue. That is a very odd issue. I really have no idea where to actually go to figure out what's causing that, because that's... Well, let's just do a sanity check. Let's see that that issue is still there when we remove our filtering board. I would wager it is. Yeah, but it's a little noisier. So it's a bit masked when we put our filtering board in there, so that's just clean. And with a filtering board, it's cleaned up slightly. We're getting rid of some of the higher frequency stuff. Now, something I am curious to test is to just steal a common mode choke out of this power supply. We've got a primary side common mode choke there, and to see if that makes any difference. So I've got my soldering irons warmed up. We can just solder this in series with the entire thing, and making sure to note which direction it goes. That's quite obvious. So let's just get some tin on this. Because it would I wouldn't put it beyond this power supply to have just an undersized ground plane or something like that, just allowing as much noise to pass through the ground as it does on the power side, positive side, 8-bit side, whatever you want to call it. So common mode choke could do you some good. I don't think there's any common mode choke on the 8-bit side in the actual unit. I'm not going to bother taking it apart just to check. So we'll got that tinned. Let's just put that in series with everything. So we will get rid of that. Off you come. Come on. They make me. Oh, that's the oxidized side. There we go. Off you come. And you go on there. And I need tweezers to grab that banana plug because it's just soldered onto the board, and grabbing that off would otherwise burn my fingers to a crisp. That heated up way easier than I thought. We'll just put that on there. It's going to take about 1 year to cool down. There we go. And we'll solder our choke to our board. Pin 1, and which one is our actual ground? I don't care. Let's just solder it to everything. There we go. So that would be a filtering board with an added common mode rejections choke. As you can see, very nicely put together. I don't think there are any shorts which would ruin everything. So let's see what happens. And I made a bit of a whoopsie. But the ground lead on the positive side, so we need to connect it in what feels like the very obviously wrong way, else my electrolytic cap is going to go up in smoke and possible flames. There we go. So let's see if that makes any difference at all. We want to. Oh, that's made a significant improvement. That is significant. We're seeing 120 millivolts now. 120. That's worse than we saw before, right? I think so. Let's do one of our standardized tests. Let's do the. Let's do filter V2 or a filter CMRR. There we go. And we'll just run it through the same test as we did before. 8 ohms, and we will do zoom in on that so you can actually see something. We will do 100 milliamps on the extremely finicky voltage knob. 60, 70, 80, 100 milliamps. And I think that's better than we've seen thus far. We're seeing I'm going to call that 65 millivolts of ripple, VPP. So let's do 500 milliamps. $480, 490, that's good enough. And we're seeing, wow, that is about 30, no, what are we going to call that? We need to zoom in even further. I'm going to call that 30 millivolts. In fact, let's zoom into the same time scale so we're getting a comparable result. Yeah, I'm going to call that 30 millivolts. That's almost as good as the TTI at this particular power output, and that's definitely by far the best result we've gotten thus far out of this power supply. So 1 amp, 8 volts, and now we're seeing 35 millivolts. On 2 amps, going to be interesting once we go above 2 amps to see when that weird 50 Hz modulated crap comes through, if we're going to see any notable improvement. Now we obviously have a 50 Hz crap still there, but it's dampened down a lot because we're seeing like I'm going to call that 37. So now we're going to 3 amps, and this is where we usually start running into a lot higher noise figures, and we still do 2.9, 3.01, there we go. And now we're just shooting out, we're seeing 88 millivolts. Peak to peak noise. Still a lot better than anything else we saw. Now let's do 30 volts. That's giving us 120. Which is way better than anything we've seen before. But still not very good. Now let's do the final one at 4 ohms and 5 amps. That's 5 amps and a lot of bloody noise. We're still just 165 millivolts. So that is the common mode choke. That's doing a lot of good for us right now. Now, granted, these components aren't just random pieces picked out of this train wreck of a power supply. So you could probably do a lot better by having better components and doing proper frequency testing and what have you to see which actual values you want of this stuff. But we have gone from 500 millivolts peak to peak ripple to 165 millivolts on the maximum load of this power supply, which I think is a quite considerable improvement. We are still nowhere near as good as a good expensive real switch mode lab power supply, but we're certainly better. Certainly better. Do we have anything else we could add from this? We could try just adding this giant choke, which is going to have a lot of inductance. Just for the hell of it. Yeah, let's just add this giant choke to see if that does any good. I don't think it's... Let's make a prediction and test. I don't think this is going to do much, since the common mode choke did more good than the entire rest of the filtering circuit put together. So I think this is going to give us pretty much the same results as we're seeing right now. If anything, we're going to see marginal improvements. Place your bets. This has really, really thick lacquer on it, making a lot of smoke when I'm trying to melt through it. Seems to be some really high temperature stuff. It's not going away. Oh, come on, don't make me strip you with manual labour. That would be annoying. Yeah, that's not melting. That's a high quality choke. But we have managed to get just a bit of tin on there, so it's probably good enough. So let's put that in there. Now let's just use the paint supply for mounting while soldering, because that's easy and accessible. This is going to be so beautiful. A piece of art. That's on there. And this goes on there. We'll blob these together. And now we've got even more inductance. And this is a pretty hefty choke. And it's done absolutely nothing, because we're at 5 amps and we're seeing 160 millivolts ripple. We measured 165 before, and it's jumping around. So I would wager that we've mostly got a common mode issue here. So that begs the question is the wrong term. I don't remember. That leads me to want to dig around the junk box for even more common mode rejection chokes to see if we can actually make this even better. Try directly off mains if the 50 Hz issue is caused by the inverter. This is directly off the mains. But let's find another common mode rejection choke. And I happen to have a couple of these 8 amp rated common mode rejection filter blue thingamabobs just lying in the junk bin. So we'll stick one of these in series with this whole blob of crap and see what happens. This is becoming a bit cumbersome. But what do you not do for science? Especially the science of near-lethal cheap Chinese paint supplies, which you really shouldn't be using to begin with. When I reviewed this thing, I should have been more vocal about how potentially unsafe it is, because it really is potentially unsafe. But oh well, we all need a bit of excitement. What was more exciting than invisible death? If you go skydiving, you at least know when it's gonna happen. You know when the parachute fails. you get to fall to your death. But with this stuff, you never know. It could happen any day, any time. And I'm not going to grab that with my fingers and try to solder it. That would be a bad idea. You know, wait another year for the solder to settle. Try bigger chokes with less and thicker windings. Yeah, well, I'm thinking common mode is our enemy right here. So let's shove this rather long-winded filter into the inverter and see what happens. And that is definitely the best result we've seen thus far. We're seeing at 5 amps 60 millivolts of ripple. So the issue clearly is common mode. Common mode is poor on this thing. It's putting out crap differentially on the output. In fact, I think we can even bridge out the big cap here, have a big choke we added before, and it's not going to make much of a difference. 54 millivolts with it shorted, 58 with it not shorted. I would actually add a ceramic cap. Well, we can certainly try adding a cap. Do we have something useful on this thing? I of course don't have any new caps. What do you take me for? Rich? Perhaps we can just... what do we have which is small? These Y-class caps here look kind of reasonable. I can't make out the text on them though. That's annoying. Oh, let's just dig through to find a new ceramic cap. In my big bag of ceramic caps out of China, which are absolutely dreadful. 101, that's a tiny little thing. Let's do something in the middle of a range. Like 102 or something. Back in a sec. Alright, we're back. Yeah, I'm looking for like 102. 301. Where are my X02s? Somewhere. 682. A rather big too, but yeah. That's going to be good enough. I don't think this is going to do too much, actually, because we already have a 100 nano cap right in the end of the filter. But we'll try it. We'll just add it. I don't know. It's going to be easy to add right between the chokes there, so we will do that. Tin that. There we go. And let's see if we can manage this without desoldering everything. I don't remember what the actual result was. Oh well. Okay. Little tiny ceramic cap. So let's turn it back on, see if it makes a difference. And it did absolutely nothing. Now I'm not at all surprised because, yeah, we haven't analyzed this in any meaningful way, so it's just random guessing. But really, we're getting down to a point where the output is actually kind of acceptable. Because I think if we sweep it down, turn the voltage down, we're not going to see more noise at any stage. No, we just see less. And now we're just getting down into the noise floor testing rig at just about 2 amps of output. And now we're putting at 7.5 volts at 1.74 amps, and we're just down in the noise floor. Now the output at 0. So this is actually performing quite well now. Ooh. We do get quite a bit of noise if we actually just ram it up into the current limit. That's about 100 millivolts of noise at 5.13 amps. That's not doing bad now though. It's not doing bad at all. Now the question is, how much of this filtering stuff do we actually need, because we've got a rather ridiculous filter setup. I'm thinking let's just try and solder ourselves onto there and see if our 3.9 nanohenry common mode filter is all we actually need, because that's the one which made the biggest difference when connecting up. That one made a bigger difference than the entire rest of the setup. Now granted, we haven't tested that without these little extra caps there. I'm thinking we probably don't need any other big caps. The big electrolytic I have there isn't going to do anything, since we already have a giant amount of electrolytics capacitance in the device itself. It's like a couple of thousand microfarads. But the 100 nano could be doing something. And my little 2 micro film caps could also be doing something. Oh, come on. The PCB is falling apart. There we go. We need more solder. Plug number positive and plug number negative. So now we're just doing a common mode rejection choke and a, what's that, 68 nano or 680 nano ceramic, which I don't think is going to do anything at all about anything. And yeah, as predicted, the output is almost as good as with the entire filter setup. In fact, once we hit the current limit, we're actually seeing a somewhat cleaner output, with just about 120 millivolts of ripple. So yeah, really, the performance of this device is considerably improved by just adding a common mode rejection choke to the output, because this performance is actually quite decent. Let's get rid of a little ceramic as well, and do a full sweep test to see how the performance is compared to the other filter setups. Is that still soldered on? Yeah. We're all good to go. So we will make another row on the sheet. Zip VPP, and this is, let's just use CMRR only. Blue, CMRR only. So we will do the same thing all over again, except for load for 8 ohms, and slowly turn up the voltage. What was that peaking there? Oh well, let's not care about that. So we'll do 100 milliamps. And we are seeing... Yo, what was that? What was that giant peak there? I don't know. Doesn't seem to be coming back. Or is it? We're gonna see it's... No. We'll stick to our setup. So we're seeing... I'm going to call that 60 millivolts. And let's do 500 milliamps. Finicky. And we're seeing, I'm going to call that 65. So this is inferior to the entire big setup we had before, certainly, but it's still way better than the stock power supply. 1 amp. And we're seeing, I'm going to call that 65. And we're still seeing a degradation in performance. So let's do 1 amp. And we're still seeing about 65 millivolts. 2 amps. This is where it starts to get a bit interesting, if previous experience is to judge by. 2 amps. I'm gonna call that 70. We're still worse off than with the filter, still better off than the filter with no CMRR, and way better off than the stock power supply. 3 amps. That is... I'm gonna call that 90. And let's go to 30 volts. And I've done something wrong, because this is the test we're supposed to be doing now. Oh god, I've messed something up. What is the frequency of the ripple? Let's see. There's a lot, I suppose that's the ripple, and we've got a lot of like high frequency stuff above it. But that's at 5 microseconds per division, so we can get some cursors on that. So we will... how do you do this? We've got like the bottom of a waveform there-ish. Cursor B. What? Oh, I'm adjusting both now. Oh god. I never use cursors on this, but yeah, that's pretty much spot on, really. About 40 kilohertz, 37.3 from there to there. About 40 kilohertz. I'm not sure if that's coinciding with the switching frequency of this thing. Let's go back, try to get back to our testing setup. If the rotary encoders on this piece of crap wanted to keep up with me. And cursors off, please. Yeah, I'm going to redo a couple of these because I messed something up right about here. So we'll redo 2 amps. No, I know that's right actually, so we'll redo 3 amps. And at 3 amps we're seeing 90. And at 30 volts we're seeing 105. And let's do 5 amps. And we're seeing 100 and I'm going to call that 110. Well, that's curious. We're seeing less ripple at the highest current setting than we did with the entire big testing chain, of the entire big filter we were using before. So that must have been ringing or causing some kind of issues before. But really, all things considered, just using this common mode rejection choke is improving the quality of the output on this device quite significantly. In fact, let's just look at the waveform like that. We're seeing about 120-ish millivolts of ripple there. Let's disconnect our filter and connect straight up to the output of a power supply and see the difference. Filter going out. 500 millivolts of ripple. So, what you need in order to quickly improve the performance of this thing is something along these lines. A 3.9 millihenry common mode rejection choke. Because that's the biggest difference we've seen thus far. But I want to try putting this 100 nano cap across the output of it, because I don't think we actually have any small capacitance filtering on the output of a power supply, unless there's like some hidden little ceramic somewhere. I haven't seen it. We'll just steal this and solder it onto our plug leads. There we go, 1 lead, 2 leads. Now, I saw someone in the chat talking about something of 100 microhenry or 100 microfarad range fixing the 40 kilohertz ripple. Now, that could be right, but the 40 kilohertz ripple is not the main issue. Most of this noise is just high frequency little spikies riding atop that, probably coming out of a switching diode as it's rectifying the output. The 40 kilohertz ripple is not the biggest issue, because we have giant output capacitance already. So let's see what we get. Yeah, at the same 5 amps we're now getting 96 millivolts by just adding this capacitor, and that was 110 before. So we could try adding, this is a 10 microfarad. Let's see what that does. I would just put it on there. Yeah, taking it down to about 80. Yeah, 10 microfarad cap is not really doing anything. That's 10 microfarad connected, 10 microfarad disconnected, 10 millivolts ripple difference, not a whole lot of change going on. Oh, let's try the minuscule ceramic again. Well, hello. That's actually, this minuscule ceramic is doing way more than the big electrolytic. This is a 682, is that 68200 nanofarads? Oh, I'm so bad with my tiny caps. It's a 682, and it does a lot of good. And that is because most of this stuff is so high frequency. I wonder what happens if we put a really tiny ceramic cap across this. This is a 5. Let's see. Really super tiny one. Super duper tiny. Ah, this is difficult. And that does nothing at all. So, what else can we try? I'm not sure if I have any bigger ceramics than 682. I have a 104 here. 80 come. 104. So let's see if a 104. That's going to be like. Oh god, I have no idea. 0.1 micro, something like that. That brings down the ripple almost 10 millivolts. But the best result thus far has definitely been with the 682. And what happens if I just put my finger across there? Nothing. So it's not because I'm fingering around there. With the 682 is making a difference. 682 is definitely making a difference. Let's just solder the 682 in there with a bit more properly to see if we can actually improve this a bit further. There we go, one side, other side. No, everything's falling apart. There we go, 682 and 0.1 microfarad in parallel. Our result is 65 millivolts at 5 amps. And that is definitely the best result we've seen thus far out of a Wanptek. That's better than this entire thing. That is, above all, it's less than 100 millivolts at 5 amps, which isn't too bad. And if we turn the voltage down, the ripple just goes down. What happens if we slam it into the current limit? Yeah, it goes up a bit while it's current limiting. Current limit doesn't seem to be too well implemented on this thing. But once we go below the current limit, it drops to 65-ish millivolts, which isn't too bad, honestly. That's really not too bad. Now, I wonder if we we've tried 104, we've tried 5, and we've tried 602. Do I have any other interesting values? I've got a 203 down here, so that's going to be a bit higher than the 602, a bit lower than the 104. Let's try shoving a 203 in there as well. It's pathetic how I don't remember what the actual capacitance of this thing is off the top of my head. So we're seeing this particular setting. Let's do 5 amps exactly. We're seeing 68 millivolts. So let's see what happens. We've put our extra cap on there. It does absolutely nothing. Nothing's changing. So the 203 does nothing. I must have hit it pretty spot on with a 682, because that seems to clean it up quite well. 203 is 20 nanofarads, 104 is 100 nanofarads. Thank you, Jermaine Jacob. Did you add a discharge resistor for big caps? No, I haven't. I have not. That's probably not a bad idea to add on this thing, actually. Because it's probably not too clean if we just let it sit unloaded. Okay, I'm wrong. I just turned the load off and it's very clean just sitting unloaded, because it's just got the giant capacitance. So what's 682? If 203 is 20 nanofarads, 682 is going to be 6.8 nanofarads. Am I right in saying that? I don't have a tools handle at my disposal to just check that. Haven't set these computers up properly. But I'm going to say that the 3.9 microhenry common mode rejection choke, a 100, as well as a 6.8 nanofarad cap on the output of the Wanptek KPS305D cleans up the output significantly. And I think I'm going to do one final sweep of this little test with a filter installed, and we will go through the results in total. Clean piece of paper. So we want 100 milliamps, 500 milliamps, 1, 2, 3, 4, 5 amps. Zip, zip, and we have VPP, ripple current out, and this is with a 3.9 millihenry CMRR choke and a 100 nanofarad cap and a 6.8 nanofarad cap, like so. So these are the changes we've made to the output of the unit. So let's find out our final performance. 8 ohms load on. $100 milliamps gives us 30 millivolts. 500 milliamps gives us are we measuring properly? Are we having a bad connection? That's reading 18 millivolts. 18 millivolts, that is quite impressive, I must say. That's actually on par with some of the tests we got out of the $700 power supply. But it's going to get worse as we go up to the higher current, so let's not get too excited. 1 amp gives us 20 millivolts. 2 amps gives us 32. No, I'm going to be generous, say 30. 3 amps. And we're getting, I'm going to call that 54 millivolts peak to peak ripple and noise. And the 4 amp setting was 30 volts, I believe, because we can't get it running quite right otherwise, so we'll cheat that again, do 30 volts, and that's actually 3.66 amps. Like so. And that gives us 65. And for the 5 amps we'll cheat again, do 4 ohms. And we're getting 70 millivolts. And those are not particularly poor figures. In all honesty, these are not particularly poor figures. And we need to compare that to the test we took in the beginning with the expensive power supply. And at high current it was giving us 40 millivolts. And the lowest we saw was 20. So I'm not going to say that this is a low noise power supply, because it isn't. But if you add the components listed there to your Wanptek KPS305D, you can significantly improve its noise performance. And with that, I'm going to say thank you for watching this little rambler little stream. Goodbye, have a good night.